This online tutorial is about the Bronsted-Lowry acid-base definition and theory. In the context of acids and bases, in many cases, especially in analytical chemistry, we usually use the Bronsted-Lowry acid-base theory. While it is common to discuss the Arrhenius acid-base definition as the first modern acid-base definition at the beginning of talks about acids and bases, due to its limitations, we usually use other acid-base theories, especially the Bronsted-Lowry acid-base theory and the Lewis acid-base theory. The Bronsted-Lowry acid-base definition was proposed independently by Bronsted and Lowry in 1923. Based on the Bronsted-Lowry acid-base definition, an acid is anything capable of donating H+ or hydrogen ions, and a base is anything capable of accepting H+ or hydrogen ions. In simple words, a Bronsted-Lowry acid, or simply a Bronsted acid, is a proton donor, and a Bronsted-Lowry base, or simply a Bronsted base, is a proton acceptor. So we have the Bronsted-Lowry acid-base definition, in which acids are capable of donating H+ or hydrogen ions. Or in fact, there are proton donors. And bases are capable of accepting H+ ions. Or there are proton acceptors. For example, consider the reaction between the hydrogen chloride gas and ammonia gas, which yields ammonium chloride solid, where ammonium chloride solid is composed of ammonium and chloride ions. In this reaction, HCl gives H+ and NH3 accepts or receives that H+. So in here, HCl is donating H+ ions, and HCl acts as a proton donor. So HCl is a Bronsted acid here. On the other hand, NH3 is accepting those H+ ions. NH3 is a proton acceptor here. So NH3 here is a Bronsted base. Here it is also good to know the definitions of Bronsted acid and base by IUPAC. In IUPAC's Gold Book version 2.3.3, in the entries for the Bronsted acid and Bronsted base, we have for the Bronsted acid a molecular entity capable of donating a hydron, proton to a base. That is a hydron donor. Or the corresponding chemical species. In the case of Bronsted base, we have a molecular entity capable of accepting a hydron from an acid that is a hydron acceptor, or the corresponding chemical species. To understand these definitions, we should be familiar with the terms molecular entity, hydron, and chemical species. A molecular entity is anything identifiable as a separately distinguishable entity. For examples, atoms, molecules, ions, ion pairs, radicals, ion radicals, complexes, and so on, all can be considered as molecular entities. IUPAC considers the term molecular entity as a general term for singular entities. IUPAC uses the term chemical species for sets or ensembles of molecular entities. For example, in the case of a single water molecule, we consider the term molecular entity, while in the case of a number of water molecules, for example, a molar amount, we consider the term chemical species. So here, either we are dealing with a molecule or ion, or we are dealing with a number of molecules or ions, for example, a molar amount. In both cases, we can consider the terms Bronsted acid and also Bronsted base. What is hydron? Hydron is a general name for the H+ or hydrogen cations, without regard to their nuclear mass. It is used for H+ in its natural abundance, or where it is not important to distinguish between the isotopes. The element hydrogen is more than 98% hydrogen 1 isotope. Or proton, and less than 0.02% hydrogen 2 isotope, or deuterium. Hydrogen 1 cations are equivalent to protons, but a hydrogen 2 cation isn't equivalent to a proton. A hydrogen 2 cation is a proton and a neutron together. So, not all hydrogen ions are proton. a small fraction of hydrogen ions are hydrogen 2 ions, which are protons and neutrons together. So consideration of hydrogen ions as protons is not exact. To avoid this approximation, it is better to use the pair hydron for H plus ions. We can call H plus ions as hydrogen ions or hydrogen ions. But we usually ignore the small fraction of hydrogen 2 in natural abundance of the element hydrogen on Earth, and we consider hydrogen ions as protons. But we should keep it in our mind that not all hydrogen ions on Earth in the natural abundance are exactly protons. Here, we should also be familiar with the term conjugate acid-base pair. For example, consider the pair NH4 plus and NH3. NH4 plus ammonium ion, NH3 ammonia. NH4 plus can donate H plus yielding NH3. On the other hand, NH3 can accept H plus yielding NH4 plus. So NH4 plus and NH3 can be converted to each other by donating or accepting H plus. We consider pairs like these as conjugate acid-base pairs. NH4 plus and NH3 here together constitute a conjugate acid-base pair. NH4 plus is the conjugate acid of NH3. NH3 is the conjugate base of NH4 plus. Conjugate acids and bases are converted to each other by donating or accepting hydrogen ions. We can consider general forms for conjugate acid-base pairs. For example, we can consider HA and A minus, or let's say HA/A minus as a general form for a conjugate acid-base pair. H for the H plus that the acid can donate, and A for the first letter of the word acid. Here, HA is the Bronsted acid, A minus is the Bronsted base, HA is the conjugate acid of A minus, and A minus is the conjugate base of HA. Also, we can consider the pair BH plus and B, or BH plus/B as a conjugate acid-base pair, where H is for the H plus that base can accept, and B is for the first letter of the word base. So we see we can consider many general forms like these for conjugate acid-base pairs. Here, absolute charges are not important, but the conjugate acid always has one unit of positive charge more than the base. Or, in other words, the conjugate acid has one unit of negative charge less than the base. Also, the conjugate acid has one H more than the base. In all of these conjugate acid pairs, conjugate acid and conjugate base can be converted to each other by donating or accepting H+ ions. In the context of acids and bases, acid-base reactions or reactions between acids and bases are very important. Based on the Bronsted-Lowry acid-base definition, an acid gives or donates H+, while a base receives or accepts an H+. So, in an acid-base reaction, we will have transfer of H+ ions from acid to base. Or, based on the Bronsted-Lowry acid-base definition, acid-base reactions are in fact proton transfer reactions. For example, consider this example. In this example, H+ or proton is transferred from HCl to NH3. So in this reaction between a Bronsted acid and a Bronsted base, we also have the transfer of proton. This is both an acid-base reaction based on the Bronsted-Lowry acid-base definition and also a proton transfer reaction. Here, it is also important to notice that in an acid-base reaction, Bronsted acid and Bronsted base react each other to produce their conjugates. The general form can be written like this. Bronsted acid and Bronsted base react each other and yield their conjugates. For example, in this reaction, HCl Bronsted as a Bronsted acid and NH3 as a Bronsted base react each other and produce NH4 plus and Cl minus. Cl minus is the conjugate base of the HCl, and NH4 plus is the conjugate acid of NH3. So, this acid and this base react each other and produce their conjugates. As another example, we can consider these pairs of acids and bases. We can write this reaction. HA and B yields A minus and BH plus. Here, HA acts as a proton donor and B acts as a proton acceptor. HA is our Bronsted acid and B is our Bronsted base. This is an acid-base reaction between HA and B. This is also a proton transfer reaction. The products are A minus and BH plus, where A minus is the conjugate base of HA and BH plus is the conjugate acid of the B. So we see acid and base react each other and yield their conjugates. Another important term here to consider is the term amphoteric. A chemical species that can behave both as an acid and as a base is called amphoteric. For example, consider HCO3 minus or hydrogen carbonate in aqueous solutions. In aqueous solutions, hydrogen carbonate can donate H minus to produce carbonate ion, CO3 2 minus. It can also accept an H plus cation to yield H2CO3 or carbonic acid. So in aqueous solutions, hydrogen carbonate HCO3 minus can act both as a Bronsted acid like this and also a Bronsted base like this. So we can call HCO3 minus an amphoteric species. It is amphoteric. It is important to notice that the Bronsted-Lowry acid-base theory doesn't limit acids and bases and their reactions to aqueous solutions. The Arrhenius acid-base definition limits acids and bases and their reactions to water, to aqueous solutions. And this is a serious disadvantage for the Arrhenius acid-base definition. But this is not the case for the Bronsted-Lowry acid-base theory. Based on the Bronsted-Lowry acid-base theory, the medium can be water or anything, or any other thing. For example, other solvents and also the gas form. So the Bronsted-Lowry acid-base definition is much more general than the Arrhenius acid-base definition. And this is a very important advantage for the Bronsted-Lowry definition. This means that not only we can consider acids and bases and their reactions in many different situations, in aqueous solution, in non-aqueous solution, in gas form, and so on, but also we can compare acid-base behavior of substances in those different situations. These are important in the context of acids and bases. I will talk about these topics in next tutorials. This is the end of this online tutorial. I hope you find it useful.